This section is going to focus on reaction mechanisms. So far when we've looked at chemical reactions, we generally describe the reactants and the products, describing all of them in one reaction. But in reality, the probability of more than 3 molecules colliding at the same time with the correct energy and orientation is negligible. So most reactions occur in a series of smaller steps that each individual step involves 1, 2, or maybe 3 molecules. And describing that series of smaller reactions that add up to the overall reactions is called a reaction mechanism. If we know the rate law of the reaction, it helps us understand the sequence of events that takes place in the mechanism. So let's look at an example. So here we have an overall reaction, hydrogen gas plus 2 iodine monochlorides gives 2 hydrochloric acids plus molecular iodine. The mechanism, though, instead of having all 3 of these molecules collide with each other, the hydrogen collides with 1 iodine monochloride to form 1 hydrochloric acid and a hydroiodic acid. Then the hydroiodic acid reacts with a second iodine monochloride and gives a second molecule of hydrochloric acid, and then that's when we get our iodine. So these steps in our mechanism are called elementary steps, and that means that they can't be broken down into simpler steps. Those are the molecules actually directly interacting in that manner without anything else happening. Now, in this mechanism that we just talked about, notice that hydroiodic acid is formed and then reused. So product in step 1, reactant in step 2. It's made, then consumed. It doesn't show up in the overall reaction because for a reaction mechanism to be valid, it has to add up to the overall reaction. The term for something that's produced in an earlier step and then used up is an intermediate. So here hydroiodic acid is an intermediate in the reaction mechanism for this overall reaction. More terms for you. The number of reactant particles in an elementary step is called its molecularity. So a unimolecular step involves 1 particle. Bimolecular step involves 2 particles. Notice they might be the same type of particles. There are just 2 of them interacting with each other. And termolecular steps involve 3 particles. They are very rare in elementary steps. Elementary steps are primarily made up of unimolecular and bimolecular steps. And unlike an overall reaction, we can determine the rate law of an elementary step just based on its reaction. So if we have A going to products, its molecularity is 1, and its rate is just the rate constant for that step times its concentration. If it's a bimolecular step of 1 molecule reacting with an identical molecule, it's a bimolecular step, and the rate law is K times A squared. If it's 2 different molecules reacting, it's also a bimolecular step. Their rate is K times A times B. And then we can get into the rare steps as well. So, unlike normal reactions, for elementary steps, you can determine the rate law from the step. Now, for most reactions, there's one step that is slower, significantly slower than the rest. And product production can't occur any faster than that slowest step. You can think of it as when you're coming up to a construction zone, often the merging into one lane is the slow step there. It clogs up everything behind there, but once everybody's merged, traffic starts moving quite quickly. The slow step is this actual merging part. And that slow step is also called the rate determining step. It's going to have the largest activation energy and take the most time. And, this is important, the rate law of the rate determining step determines the rate law of the overall reaction. So if you know the mechanism, you can determine the overall rate, because the slow step, the rate determining step, will determine your rate law for your overall reaction. Your mechanism is not valid if your slow step doesn't match what the experimentally determined rate is. So let's look at another example. So here we have a two-step mechanism. Our slow step is first. We have two NO2 molecules reacting with each other to form this intermediate here and a product. Then our intermediate reacts with our other reactant to form our other products. Actually, to form one of the reactants and the product. The first step is the slow step. It has the higher activation energy. The second step is fast, has a lower activation energy. First step is the rate determining step. And notice we have our rate of our slow step here is a rate constant times NO2 squared, because it's two NO2s reacting with each other. And our overall rate law is the same as our rate determining steps rate law. In order to validate a mechanism, we can't prove a mechanism because you can't actually watch it react. But we need these two conditions to be met to validate it. The elementary steps need to sum up to the overall reaction, and the rate law predicted by the mechanism needs to be consistent with the experimentally observed rate law. Now, sometimes there's a fast initial step, and then the rate determining step can contain intermediates. If a previous step is rapid, it will reach equilibrium, and at equilibrium the forward and reverse reaction rates are equal, and so you can kind of back calculate what the rate law for the reaction is by substituting things in. So let's work through an example, because I think that's a lot easier to understand than working this through. So here's our reaction. We have this first fast initial step where our NO goes to N2, or two NOs go to N2O2. And then our slow step is this one where hydrogen reacts with our intermediate to form water and some products. So here's our overall rate, or our overall reaction. How do we determine if our rate for our slow step is consistent with our rate for our overall reaction? Well, what we're going to do is solve backwards for our intermediates and plug things in. So for step one, back here, our fast step, we know that our K1, our forward rate, times NO squared, because there's a 2 there and it's an elementary step, is equal to whatever our K reverse is times our N2O2. So if we're going this way, and because they're at equilibrium, they're equal to each other. So our forward rate is equal to our reverse rate. So we can solve for our concentration of N2O2 using our NO2 squared, which is one of our reactants. So that can be in our overall rate. And so instead of writing N2O2, we're going to plug in NO squared. So for this, we're plugging it in, which you can see then matches what's down here for our observed rate. And don't worry too much about the K1, K minus 1. Those all have to be solved for, are given to you individually, and often in the overall rate law they just get kind of shoved together into one K value. So let's practice. Determine the overall reaction, the rate determining step, the rate law, and identify all intermediates in the following mechanism. So let's find our overall reaction first. All we have to do there is add together our reactions. So we have, as a intermediate, we're forming B and then using it up. So B is an intermediate. So our overall reaction, we have 2A's plus B2 goes to 2AB. There's our overall reaction. The rate determining step is the slow step, which in this case is our first step. So our rate law is going to be equal to our rate constant K times our concentration of A times our concentration of B2. And that's just because we have this elementary step. So we have overall reaction, rate determining step, here's our rate law, and we identified our intermediates. There we go. Here's a little bit more difficult one. Possible mechanism for the overall reaction is found below. What is the rate law based on this mechanism? So why don't you pause the video, work it out, and then I will solve it for you. So for our for forming our intermediate here, we know that K times NO, or sorry, K1 times NO times Br2 is equal to K minus 1 times NOBr2. So, and then our slow step, we have K times NOBr2 times NO, both to the first. So then we can plug in from up here. We know that our NOBr2 is equal to K1 over K minus 1 times NO times Br2. So if we plug that in, we're going to get, this is K2. We're going to get K2, K1 over K minus 1 times NO Br2. And then there's a second NO there, so I'm just going to write NO squared. So that gets me letter C.